Imagine standing far above our galaxy, far beyond the reach of any spaceship, watching the Milky Way from a silent distance. From there, it looks calm and graceful, a vast glowing disk slowly turning in the darkness, made of hundreds of billions of stars. Like cars moving smoothly on a giant cosmic highway, almost everything flows in the same direction. Star after star follows the same path, orbiting the galactic center, as if they all agreed on the rules long ago. At first, nothing feels strange, but then you look closer. Hidden among this orderly motion are a few stars that do not belong to the flow. While the galaxy turns one way, these stars move the other way. They orbit backward, against the direction of billions of neighboring stars. It is subtle. You would never notice it by just looking at the night sky. But once you see it, you cannot ignore it. These stars are not drifting randomly. They are not lost. They are moving with purpose, cutting through the galaxy like swimmers going upstream in a powerful river. This is not a mistake. This is not chaos. It is a clue. In space, motion is memory. The way something moves tells a story about where it came from and what it has survived. When a star refuses to follow the galaxy's rotation, it is quietly telling us that something dramatic happened long ago, something violent enough to bend the rules of an entire galaxy. Tonight, we are going to uncover one of the quietest and most fascinating mysteries of the universe: why some stars orbit the galaxy backwards. What force was strong enough to flip their motion? What kind of ancient events could leave behind stars that still move against the flow billions of years later? These backward-moving stars are not rebels by choice, they are survivors. They carry ancient memories locked inside their motion, memories from a time when galaxies collided, merged, and tore each other apart. Long before Earth existed, before the Sun was born, before the Milky Way looked the way it does today. By studying these stars, astronomers are not just tracking movement, they are reading the fossil record of the universe. Each backward orbit is like a scar left behind by a cosmic collision, a reminder that galaxies do not grow peacefully. They grow by consuming others, by surviving chaos, and by slowly settling into order. This story is not about rare stars doing something strange. It is about how galaxies are built, how destruction leads to creation, how the universe remembers its past even when the evidence seems invisible. So as we begin this journey, remember this: the galaxy you see today is not the galaxy that always existed. It is the result of countless ancient events, written not in light, but in motion. And some stars are still telling that story by going the wrong way. To understand why some stars move backward around the galaxy, we first need to understand how the galaxy normally works. Before we talk about broken rules, we must clearly see what the rules are. The galaxy is not a random cloud of stars flying in all directions. It has structure, order, and motion that has been shaped over billions of years. Think of it less like fireworks exploding and more like traffic flowing through a massive, invisible city in space. Our galaxy is shaped like a giant flattened disk. At its center is a dense region packed with stars, gas, and dust. From that center, spiral arms stretch outward, filled with younger stars, glowing nebulae, and clouds where new stars are still being born. When you zoom out and look at the galaxy as a whole, it resembles a slowly spinning wheel made of light. Almost everything in that wheel is moving in the same direction, following the same general path around the center. This shared motion is not an accident. It is the natural result of how galaxies form. Long ago, before stars even existed, the galaxy began as a massive cloud of gas and dark matter. Gravity pulled this material inward, causing it to collapse. As it collapsed, it started to spin, just like a figure skater pulling in their arms. That spinning motion never disappeared. Instead, it became the foundation of the galaxy's structure. When stars formed inside this spinning cloud, they inherited its motion. They were born already moving in the same direction as the material around them. Over time, billions of stars settled into stable orbits, all circling the center in a shared flow. This is why, when astronomers observe the galaxy today, they see a strong pattern. Most stars orbit in the same direction, at roughly similar speeds, following smooth paths around the galactic center. This is what we call normal motion. Normal does not mean boring. It means predictable. It means ordered. In this system, stars closer to the center complete their orbits faster, while stars farther out move more slowly, but the direction stays the same. Imagine cars on a circular highway. Some lanes move faster, some slower, but everyone is driving clockwise. That shared direction keeps the system stable. It prevents constant collisions and chaos. This shared motion matters more than it might seem. When stars orbit in the same direction, their gravitational interactions remain gentle. They pass by one another without violent encounters. Over billions of years, this stability allows spiral arms to exist, gas clouds to survive long enough to form new stars, and planetary systems to remain intact. The galaxy becomes a long-lasting structure instead of a short-lived mess. The rotating galactic disk is the heart of this system. It is thin compared to its width, like a cosmic pancake. Most of the stars we see in the night sky, including our sun, live inside this disk. They move along smooth, nearly circular paths, quietly following the galaxy's rotation. From within the disk, everything feels calm. The motion is so steady that we do not feel it at all, even though we are traveling through space at enormous speeds. This calmness can be misleading. Because the galaxy looks stable today, it is easy to assume it has always been this way. But the smooth rotation we see now is the result of time, immense amounts of time. Early in its life, the galaxy was more chaotic. Gas clouds collided, stars formed rapidly, and gravity pulled everything into shape. Over billions of years, random motions were slowly smoothed out. What remained was an organized system where most stars share a common direction of motion. This shared direction acts like a baseline. It gives astronomers a reference point. Once you know how most stars move, anything that does not follow that pattern immediately stands out. A star moving faster than expected, slower than expected, or in a different direction becomes interesting. It becomes a question. Backward motion is the most extreme example of this. When a star orbits in the opposite direction of the galactic disk, it is not just slightly off, it is completely out of sync with the system. It is like a single car driving the wrong way on a circular highway where everyone else is moving together. That kind of motion cannot happen quietly. It demands an explanation, but before we search for that explanation, we must fully respect how strong the normal pattern is. The galaxy strongly prefers order. Gravity works over time to erase chaos. Stars that move wildly or unpredictably tend to settle into smoother paths, or they get flung outward into more distant regions. The fact that backward-moving stars still exist today tells us something powerful. Whatever caused them to move this way must have been strong enough to resist billions of years of gravitational smoothing. This is why understanding normal motion is so important. Without it, backward motion would mean nothing. It would just be another direction among many. But in a galaxy where almost everything moves together, backward motion becomes a message from the past. The galactic traffic system sets the rule. Stars are expected to orbit in the same direction, within the rotating disk, following paths shaped by gravity and time. This rule defines what we call a stable galaxy. It defines what we experience as normal cosmic behavior. Only after setting this rule can we truly appreciate how strange it is when a star breaks it. And once a rule is clearly defined, the story becomes much more interesting when we discover who broke it, how it happened, and what it reveals about the hidden history of the galaxy itself. When astronomers say that some stars orbit the galaxy backwards, they are not using dramatic language. They are describing something very specific, very real, and very important. But the phrase can easily be misunderstood. So before we go any deeper into this mystery, we need to slow down and clearly understand what backward actually means in the context of a galaxy. First, let's talk about direction. In our galaxy, there is a dominant direction of motion. Most stars move around the galactic center in the same overall direction. This is called prograde motion. Prograde simply means moving with the main flow. It does not mean fast or slow. It only describes direction. If the galaxy rotates clockwise when viewed from above, then a star moving clockwise is prograde. Retrograde motion is the opposite. A retrograde star moves against the main flow. If most stars go clockwise, a retrograde star goes counterclockwise. That is all it means. No equations, no complicated physics, just direction. An easy way to imagine this is traffic on a circular road. Picture a massive roundabout with millions of cars driving smoothly in one direction. Some cars are in inner lanes, some in outer lanes, some go faster, some slower. But everyone is moving the same way. That is prograde motion. Now imagine one car driving the wrong way around the circle. It is not wandering randomly. It is not stopped. It is moving smoothly and deliberately, but in the opposite direction. That car is retrograde. This is exactly how backward orbiting stars behave. They are not tumbling through space. They are not zigzagging. They follow clear, stable paths around the galaxy, just in the opposite direction from most stars. Their motion is organized, predictable, and long-lasting. That is why astronomers find them so fascinating. Another helpful analogy is a river. Imagine a wide river flowing steadily downstream. Leaves, boats, and branches all move with the current. That is the normal flow. Now imagine a fish swimming upstream. The fish is not lost. It is not being pushed randomly. It is swimming with intention, using energy to move against the current. From above, it would clearly stand out because everything else is going the other way. Backward orbiting stars are like those upstream swimmers. They stand out not because they are chaotic, but because they are different from the flow around them. This leads us to an important point. Backward does not mean wrong. It does not mean broken, and it definitely does not mean impossible. The galaxy does not have a built-in rule that forbids stars from moving in the opposite direction. Gravity allows many kinds of orbits. What makes backward motion unusual is not that it cannot happen, but that it usually does not happen during normal galaxy formation. When stars form from rotating gas clouds inside a galaxy, they naturally inherit the direction of that rotation. So most stars end up moving together. That is why retrograde motion immediately raises questions. Not because it violates physics, but because it suggests a different origin. One of the biggest misunderstandings people have is thinking that backward orbiting stars somehow turned around after forming, as if they changed their minds. That is not how it works. Stars do not suddenly reverse direction on their own. There is no cosmic brake pedal or steering wheel. Changing the direction of a star's orbit requires enormous gravitational forces acting over long periods of time. So when astronomers see a star moving backward, they do not ask, why did this star decide to go the other way? They ask, where did this star come from? Another common misunderstanding is the idea that backward stars are unstable and short-lived. In reality, many of these stars have been orbiting the galaxy this way for billions of years. Their paths are stable. Their motion is smooth. If you could speed up time and watch them orbit, you would see graceful, repeated loops, not erratic wandering. This stability is crucial. It tells us that backward motion is not a temporary accident. It is a long-term condition. Something placed these stars on these paths long ago, and gravity has kept them there ever since. It is also important to understand that backward motion is always defined relative to something else. There is no universal forward or backward in space. There is only motion compared to a reference frame. In this case, the reference frame is the galaxy itself, specifically its rotating disk, When we say a star moves backward, we mean backward relative to the galaxy's main rotation. This might sound like a small detail, but it matters. Without a reference point, the concept of backward would be meaningless. The rotating disk gives us that reference. It is the shared motion of billions of stars that defines what we call normal. Another helpful analogy is a crowd moving through a large circular plaza. Imagine thousands of people walking calmly around the plaza in the same direction. You could predict their movement. Now imagine one person walking just as calmly, but in the opposite direction. They are not panicking, they are not lost, but their movement immediately tells you they have a different purpose or origin. Backward stars are like that person in the crowd. They are part of the galaxy, but they did not grow up following the same flow. It is also worth clearing up a common sci-fi idea. Backward motion does not mean a star is somehow resisting gravity or breaking physical laws. Gravity still controls everything. The star still obeys the same rules as every other object in the universe. The difference lies in the history of how that orbit was created, not in how it functions today. In fact, gravity is the reason backward orbits can exist at all. If a star enters a galaxy from outside, gravity can capture it. Once captured, the star keeps whatever direction it originally had. Gravity does not care which way something spins. It only cares about mass and distance. This brings us to an important realization. Backward motion is not random motion. Random motion would look messy. It would have no clear pattern. Backward stars, however, show strong patterns. They often travel in groups. They share similar paths, they appear in specific regions of the galaxy. These patterns tell astronomers that backward stars often have shared origins. So when we talk about backward or retrograde motion, we are not talking about chaos. We are talking about a different story written in motion. Understanding this difference is essential. Without it, the mystery loses its meaning. Backward stars are not strange because they go the other way. They are strange because they move with purpose, stability, and memory in a system where almost everything else shares the same direction. This sets the stage for everything that comes next. Now that we know what backward orbit really means, we can begin asking the deeper questions. How did these stars get there? What events were powerful enough to place them on these paths? And what do these silent backward journeys tell us about the violent and fascinating history of our galaxy? Only by understanding the meaning of backward motion can we begin to understand why it exists at all. To understand backward orbiting stars, it is not enough to know how they move. We also need to know where they live inside the galaxy. Location is not a small detail. In astronomy, location often explains history, and when it comes to stars that move against the galactic flow, their position tells us almost everything we need to know. At first glance, the galaxy looks simple, a bright disk of stars with spiral arms, glowing softly in the dark. But this is only the most visible part. The Milky Way is not a flat object. It is layered, like a vast cosmic city, with neighborhoods stacked inside one another. Each layer has its own rules, its own population of stars, and its own story. The place where most stars live is the galactic disk. This is the thin, rotating plane that gives the galaxy its familiar spiral shape. The disk is crowded, bright, and busy. Stars here follow smooth, orderly paths around the galactic center. They mostly move in the same direction, like synchronized dancers circling a stage. Our Sun lives here, along with most of the stars visible to the naked eye. Backward orbiting stars are rarely found in this calm, orderly disk. That alone tells us something important. If backward motion were common or easy to produce, we would see many such stars mixed in with normal stars near the galactic plane. But we do not. Instead, backward stars tend to live above and below the disk, far from the crowded center. They belong to a very different region of the galaxy known as the halo. The galactic halo is vast, faint and quiet. It surrounds the disk like a huge invisible bubble. While the disk is thin and bright, the halo is wide and sparse. Stars in the halo are spread out, sometimes tens of thousands of light years above and below the disk. From Earth, many of them are too faint to see without powerful telescopes. This is where backward orbiting stars feel most at home. The halo is not dominated by shared rotation in the same way the disk is. Stars here move in many different directions, on elongated and tilted paths. Some dive toward the center and then swing far outward again. Others pass above and below the disk like long, slow pendulums. The halo is a place where motion remembers the past instead of following the present. Why does this matter? Because the halo is not where stars usually form. Most stars are born in dense clouds of gas inside the galactic disk. The halo has very little gas, which means very little star formation. So when we find stars in the halo, especially ones with unusual motion, it strongly suggests that they did not form there. They arrived there. Between the thin disk and the halo lies another important layer called the thick disk. This region is harder to notice but plays a key role in the story. The thick disk is puffier than the thin disk and contains older stars. These stars still mostly follow the galaxy's rotation, but their orbits are slightly tilted and more stretched out. Some backward-moving stars appear near this region, but even here they stand out. The thick disk still prefers order. Retrograde motion is rare. When it appears, astronomers treat it as a sign that something external interfered with the galaxy long ago. To visualize this layered structure, imagine the galaxy as a glowing pancake floating in space. The pancake itself is the thin disk. Slightly above and below it is a thicker, fuzzier layer. That is the thick disk. Surrounding everything is a huge, dim cloud, extending far outward in all directions. That is the halo. Backward orbiting stars live mostly in that outer cloud. This location is not accidental. The farther you move from the galactic center and disk, the weaker the influence of orderly rotation becomes. The disk acts like a stabilizing force. Over time, stars near the disk tend to align their motion with it. Stars far away feel less of this influence. Their original motion can survive longer. This is why backward stars are more common far from the center. The outer regions of the galaxy preserve ancient motion like a deep freezer preserves fossils. Close to the center, chaos and gravity smooth things out. Far away, history survives. Another reason location matters is gravitational interaction. In the crowded disk, stars constantly pass near each other. Gas clouds, spiral arms, and gravitational waves gently reshape orbits over billions of years. These interactions slowly erase extreme motions. A backward-moving star inside the disk would eventually be nudged toward normal motion or thrown out entirely. In the halo, these interactions are rare. Stars are isolated. They travel vast distances without close encounters. Their unusual orbits remain intact for billions of years. This makes the halo the perfect hiding place for stars with strange histories. This is also why astronomers pay so much attention to halo stars. They are ancient. Many formed early in the universe, long before the galaxy settled into its current shape. Some are remnants of smaller galaxies that were torn apart and absorbed by the Milky Way. Their stars were scattered into the halo, carrying their original motion with them. Backward motion is especially common among these immigrant stars. When a small galaxy falls into a larger one, it does not magically flip its stars to match the new system. Those stars keep moving the way they always did. If the incoming galaxy approached from the opposite direction, its stars will orbit backward once captured. Over time, the original galaxy is destroyed, but the stars remain, spread out along their original paths. This is why location acts like a crime scene. Disk stars tell us about calm growth. Halo stars tell us about violence. Backward stars, especially in the halo, are evidence of ancient collisions and mergers. The outskirts of the galaxy push this idea even further. Far beyond the visible disk, the halo blends into deep space. Here, stars move on the longest, slowest orbits. Some take hundreds of millions of years to complete a single loop around the galaxy. These distant stars are almost untouched by internal galactic processes. Finding backward orbiting stars here is like finding pages from a very old book that was never edited or rewritten. They tell us what the galaxy used to be, not what it is now. This is why astronomers say location matters as much as motion. A backward orbiting star near the galactic center would be shocking and difficult to explain. A backward orbiting star in the halo makes sense. It fits the larger story of galactic evolution. So when we ask where these backward stars are found, the answer is not just a map, it is a timeline. They live far from the center because distance protects memory. They live in the halo because the halo is where the galaxy keeps its past. Understanding this prepares us for the next step. If these stars did not form where they are, and if their motion reflects ancient events, then the real question becomes unavoidable. What happened to put them there? And once we ask that, we are forced to confront the violent history of galaxies themselves. To uncover the true meaning behind backward orbiting stars, we need to look at something very basic and very powerful. We need to understand how stars are born. Because the moment a star is born, it already carries a memory. That memory is motion. And once a star is formed, that motion is extremely hard to erase. Stars are not born in isolation. They do not appear suddenly in empty space. Every star begins its life inside a cloud. These clouds are enormous, cold regions filled with gas and dust drifting through a galaxy. Over time, gravity pulls parts of these clouds together. As the material collapses inward, it heats up, compresses, and eventually ignites nuclear fusion. A star is born. This process happens everywhere in the galactic disk. Spiral arms are especially rich in these star-forming clouds. But while this process may look calm from a distance, it follows very strict rules. One of the most important rules is conservation of motion. The gas clouds that form stars are already moving. They are part of the galaxy's rotating disk. They orbit the galactic center, just like everything else in the disk. When a cloud collapses to form a star, it does not forget this movement. The newborn star inherits the motion of the cloud it came from. It begins its life already traveling around the galaxy in the same direction as its neighbors. This is why most stars move together. They were born together from the same rotating material inside the same galactic system. Their motion is not something they chose, it is something they inherited, like an accent passed down through generations. Even billions of years later, that inherited motion remains. This is what astronomers mean when they say stars are not born equal. Some stars are born inside the calm, rotating disk of a galaxy. Others are born in very different environments. Some are born in small galaxies with their own rotation, their own orientation, and their own history. When those environments collide or merge, the stars do not suddenly reset. They keep moving the way they always did. This is where backward motion becomes meaningful. When astronomers observe a star whose motion does not match the galaxy around it, they immediately suspect that it did not form there. Motion becomes a test of belonging. A star that shares the galaxy's rotation likely grew up inside it. A star that moves against that rotation is an outsider. This does not mean the star is strange in itself. Physically, it is normal. It burns hydrogen, shines steadily, and follows gravity like any other star. What makes it different is its past. Think of it like hearing a voice in a crowd. Everyone around you speaks with the same accent. Then you hear one voice that sounds different. That voice immediately tells you something. Not that the person is wrong, but that they came from somewhere else. Motion works the same way in the galaxy. Backward orbiting stars speak with a different accent. Their motion does not match the local flow. It does not align with the rotating disk. That mismatch is the first big clue that something unusual happened long ago. This is why astronomers often describe motion as a fingerprint. A fingerprint does not tell you everything about a person, but it tells you where they have been and whether they belong to a certain group. Stellar motion works the same way. It is incredibly difficult to change a star's orbit completely. You need massive gravitational forces acting over long periods of time. Because of this, a star's motion tends to preserve its origin even when everything else changes. Color can change as a star ages, brightness can change, position can change, but motion is stubborn. It remembers. So when scientists see stars moving backward, they do not see randomness. They see evidence. They see a fingerprint that does not match the galaxy's main population. This leads to another important realization. Backward stars are not rare accidents. They are survivors of earlier structures. They are stars that were born under different rules, in different rotating systems, long before they became part of a larger galaxy. This also explains why backward stars are often very old. Many of them formed billions of years ago, when the universe was younger and galaxies were smaller and more chaotic. Small galaxies formed stars early. Later, those small galaxies were pulled apart and absorbed by larger ones. The stars survived the destruction, but their original motion remained. This is why backward motion often comes in groups. Astronomers sometimes find clusters or streams of stars that all move backward together. They share similar speeds, directions, and orbital shapes. This strongly suggests a shared origin. These stars were once part of the same system. They were born together, traveled together, and were captured together. The galaxy we see today is the result of countless such events, and this is where the idea of not born equal becomes powerful. The Milky Way is not a single family. It is a blended archive of many families that merged over time. Most of its stars were born inside it. Some were adopted. Backward stars are the adopted ones. They are not mistakes, they are records. They are physical evidence that the galaxy did not form quietly. It grew through encounters, collisions, and assimilation. Another misunderstanding worth clearing up is the idea that backward motion means a star was somehow pushed or flipped later in life. While gravitational interactions can modify orbits, fully reversing a star's direction inside the disk is extremely unlikely. The disk is too stable, too orderly, too efficient at smoothing motion. So when we see a star whose motion completely opposes the galaxy's rotation, the simplest explanation is usually the correct one. That star was born elsewhere. This is why astronomers trust motion so deeply. It is one of the most reliable indicators of origin. It does not lie easily. It cannot be faked without enormous forces. In a way, backward stars are time travelers, not because they move through time, but because they carry ancient conditions into the present. They move today the way they were set in motion billions of years ago. Understanding this changes how we see the galaxy. It stops being a single object and starts feeling like a living record, a structure that remembers where it came from through the motion of its stars. So the first big clue is simple but profound. Stars inherit motion at birth. When that motion does not match the galaxy they live in, it tells us the star does not share the galaxy's origin. Backward orbiting stars are not rebels, they are witnesses, and their motion is the fingerprint that proves it. To truly understand why some stars orbit the galaxy backward, we have to confront a truth that feels uncomfortable, but unavoidable. Galaxies are not gentle builders. They are not peaceful cities that grow quietly over time. Galaxies grow by eating other galaxies. This process is known as galactic cannibalism, and it is one of the most important forces shaping the universe. In the vast emptiness of space, galaxies are not isolated islands. They live in groups, clusters, and neighborhoods bound together by gravity. Over billions of years, gravity pulls these galaxies toward one another. Larger galaxies exert a stronger gravitational pull. Smaller galaxies, especially dwarf galaxies, are the most vulnerable. They slowly drift inward, pulled like moths toward a flame they cannot escape. This is how galactic cannibalism begins. a small galaxy approaches a larger one. At first, nothing dramatic happens. From a distance, the small galaxy continues to rotate normally, its stars calmly orbiting its own center. But as it gets closer, the gravity of the larger galaxy begins to interfere. The small galaxy stretches. Its outer stars feel a stronger pull than its inner stars. Slowly, the galaxy begins to unravel. Gravity becomes a cosmic trap. Once the small galaxy crosses a certain boundary, there is no way out. Its stars are captured by the larger galaxy's gravitational field. But here is the crucial detail. Those stars do not instantly adapt to their new home. Gravity does not erase their past, it only redirects it. The stars of the smaller galaxy keep moving the way they always did. If the smaller galaxy was rotating in a direction opposite to the larger galaxy's disk, its stars will continue moving that way even after being captured. They are now inside a new system, but they carry the motion of their original system with them. This is how backward orbiting stars are born. From the outside, this process looks violent, but from the perspective of individual stars, it is slow and silent. There are no explosions, no sudden flashes of light. The destruction of a galaxy can take hundreds of millions or even billions of years. During that time, stars are gently peeled away, stretched into long streams, and scattered into new orbits. These streams are some of the clearest scars left behind by galactic cannibalism. When a galaxy is swallowed, it does not disappear cleanly. Its stars form long, thin rivers that wrap around the larger galaxy. These stellar streams trace the original path of the doomed galaxy. They are like ghostly outlines of something that once existed, but is now gone. Backward motion is often found within these scars. Astronomers see groups of stars moving together, all sharing similar backward or tilted orbits. These stars are not random. They are family members, survivors of the same destroyed galaxy. Their shared motion is the evidence that they were once bound together before gravity tore their home apart. This is why backward stars are so important. They are not just oddballs, they are proof. They prove that the galaxy did not form in one smooth event. They prove that it grew by absorbing smaller systems. They prove that collisions are not rare accidents, but a normal part of cosmic life. In fact, this process is still happening today. The Milky Way is currently in the process of consuming smaller galaxies. Some are already stretched into streams. Others are still intact, but doomed. Over time, they will be fully absorbed, their stars added to the halo, carrying whatever motion they had before the encounter. This also explains why backward stars are often found far from the galactic disk. When a small galaxy is torn apart, its stars are flung into wide, looping orbits. They do not settle neatly into the disk. Instead, they form a loose halo around the galaxy, preserving their unusual motion. The disk is orderly because it formed from rotating gas that had time to settle. The halo is messy because it is built from leftovers, and backward stars are part of those leftovers. Another key detail is that galactic cannibalism is not symmetrical. The larger galaxy survives mostly intact. The smaller one does not. Its structure is erased, its identity is lost. Only its stars remain, scattered and mixed into a much larger system. This is why backward motion feels so haunting. It is the last remaining sign of something that no longer exists. The stars are still there, but their original galaxy is gone. This makes the universe feel very different from how it is often imagined. We like to think of space as calm and timeless, but on large scales, the universe is restless and violent. Galaxies collide. They tear each other apart. They steal stars, gas, and dark matter. Over cosmic time, destruction is the main method of growth. Even our own galaxy is a product of this violence. The Milky Way did not form fully grown. It started small. Over billions of years, it consumed smaller galaxies, growing larger and more massive with each encounter. Every backward star we see today is a reminder of one of those encounters. This also explains why astronomers sometimes describe the galaxy as an archaeological site. The disk shows the present. The halo shows the past. Backward stars are fossils embedded in motion. It is important to understand that this process does not violate any laws of physics. It is not chaos for the sake of chaos. Gravity is simply doing what gravity does. It pulls mass together. On small scales, this forms stars and planets. On large scales, it builds galaxies by tearing others apart. This is why galactic cannibalism is not an exception. It is the rule. In the early universe, galaxies were much closer together. Collisions were more common. Mergers happened frequently. The universe was smaller, denser, and more crowded. Many of the backward stars we see today are relics from that early, violent era. They have been orbiting silently ever since. Understanding this changes how we see backward motion. It stops being mysterious in a confusing way and becomes mysterious in a meaningful way. These stars are not defying the galaxy. They are obeying gravity exactly as they always have. They are simply following a different history. So when we talk about galaxies eating galaxies, we are not using metaphor for drama. We are describing a fundamental process that shapes the universe, a process that leaves scars, fingerprints, and survivors behind. Backward orbiting stars are among those survivors. They are the evidence that the universe builds beauty through destruction, order through chaos, and memory through motion. And once you see the galaxy this way, you realize something powerful. The calm spiral we live in today was forged in violence, and the stars that go the wrong way are the ones still brave enough to remember it. When we talk about backward orbiting stars, we are really talking about events that happened so long ago that even the galaxy itself has almost forgotten them. These are not recent disturbances. They are echoes from deep time, from an era when the universe was younger, smaller, and far more chaotic than it is today. Billions of years ago, galaxies did not look like the calm, well-organized spirals we see now. They were rough, irregular, and constantly interacting. Collisions were not rare moments. They were part of everyday cosmic life. In those early times, the space between galaxies was smaller, and gravity pulled everything together more efficiently. Small galaxies formed quickly, and often found themselves falling toward larger neighbors. Some collided head-on, others skimmed past, only to be dragged back later. These encounters were slow, stretching over hundreds of millions of years, but their effects were permanent. Entire galaxies were torn apart, reshaped, or absorbed, their stars scattered into new orbits around a growing central system. The reason we do not see these dramatic collisions happening all the time today is simple. The universe has changed. As it expanded, galaxies moved farther apart. Space grew larger, emptier, and calmer. Major mergers became less frequent. The Milky Way, for example, is now relatively isolated compared to its early history. While it still interacts with smaller galaxies, the era of constant, violent collisions is mostly behind it. But absence of action does not mean absence of evidence. The shapes of galaxies can heal. Over time, gravity smooths chaos. Disks reform. Spiral arms appear. Irregular structures settle into familiar patterns. If you looked at the Milky Way today, you might assume it lived a peaceful life. But that calm appearance is misleading. Shape is temporary. Motion is not. This is where backward stars become so important. When a galaxy is destroyed, its shape vanishes. Its spiral arms disappear. Its core dissolves. But the stars that once belonged to it keep moving. Their paths through space remain, looping and stretching around the larger galaxy that absorbed them. Even after billions of years, those motions can still be detected. This is one of the most powerful ideas in modern astronomy. Motion survives long after form fades. Imagine an ancient city that was destroyed thousands of years ago. The buildings are gone. The walls have collapsed, but the roads remain, faintly etched into the landscape. If you know how to look, you can still trace where people once walked. Backward orbiting stars are those roads. They are the invisible pathways of long-dead galaxies. This is why astronomers often call backward stars fossils. Not fossils of bone or stone, but fossils of motion. They preserve the conditions of the early universe in the way they move through space today. Each backward orbit is a surviving fragment of an ancient collision, and these fossils are incredibly old. Many backward stars formed more than 10 billion years ago. They were already ancient when the Sun was born. They were already orbiting backward long before Earth existed. They have been silently circling the galaxy ever since, unaffected by the changes happening closer to the disk. This tells us something profound about time on cosmic scales. The galaxy you see today is only a snapshot. It is the latest version of something that has been rewritten many times. But not everything gets erased. Some information survives, hidden in places we rarely look. The halo is one of those places. Far from the bright disk, stars move slowly and interact rarely. Their orbits remain stretched, tilted, and sometimes backward. These motions act like sealed time capsules. While the inner galaxy evolves rapidly, the halo preserves ancient patterns. This is why astronomers say the galaxy has a hidden memory. That memory is not stored in pictures or shapes. It is stored in trajectories, in directions, in velocities. When scientists map the motion of stars in the halo, they are effectively reading the diary of the galaxy's youth. Backward stars are among the clearest entries in that diary. They tell us that long ago, the Milky Way collided with galaxies that approached from many directions. Some came in aligned with its rotation, others came in sideways. Some came in backwards. The ones that came in backwards left behind stars that still move that way today. Over time, the visible evidence of those collisions faded. Gas settled into a disk. New stars formed. Spiral arms grew bright and clear. The galaxy learned to look calm. But deep beneath that calm surface, the old motions never stopped. This is why modern astronomy places so much importance on studying stellar motion. Telescopes do not just take pictures anymore. They measure tiny changes in position over years. They track speed and direction. They build maps not of where stars are, but of where they're going. And when those maps reveal stars moving against the galactic flow, astronomers know they are looking at deep history. Another reason we do not easily notice these ancient collisions is that time smooths drama. What once would have looked like a spectacular crash now looks like a subtle pattern. The universe does not preserve events the way humans do. It preserves consequences. Backward motion is one of those consequences. It is also important to understand that these ancient collisions were not rare or special. They were part of how galaxies formed everywhere in the universe. Large galaxies like the Milky Way are built from many smaller pieces. Each piece adds stars, dark matter, and motion. Over time, these pieces blend together, but they never fully lose their individuality. This means that when we study backward stars, we are not just learning about our galaxy, we are learning about galaxy formation as a whole. We are seeing the universe's preferred method of building structure. Through violence, through merging, through survival, and through memory. The idea that motion can outlast form changes how we think about history itself. In human terms, we often focus on what we can see. Buildings, monuments, ruins. In the universe, the most important records are invisible unless you know how to measure them. Backward stars are invisible storytellers. They do not shine brighter. They do not announce themselves. But their movement whispers of ancient times, of collisions that reshaped the galaxy, of a universe that was once far more dangerous than it appears now. So when we say these collisions happened billions of years ago, we are not talking about distant, irrelevant events. We are talking about the very events that made our galaxy what it is. Without them, the Milky Way would be smaller, simpler, and very different. The calm spiral we live inside today is the result of that ancient chaos, and the stars that still move backward are the proof that the galaxy remembers, even when it looks like it has forgotten. They are the fossils of deep time. They are the hidden memory of a violent universe. And by learning to read their motion, we are learning to read the oldest chapters of the galaxy's story. When a galaxy is destroyed, it does not disappear quietly. It leaves behind ghosts. These ghosts are not shapes you can easily photograph, and they are not objects with clear edges. They are patterns of motion and position, stretched thin across space. Astronomers call them stellar streams, and they are among the strongest pieces of evidence that galaxies grow by tearing others apart. A stellar stream is exactly what it sounds like. It is a long, narrow river of stars drifting through space together. These stars were once part of a smaller galaxy or a star cluster that fell into a larger galaxy. As gravity pulled that smaller system apart, its stars were stripped away, one by one, stretched along its orbit like beads on a string. Over time, the original galaxy vanished, but the stream remained. These streams can be enormous. Some wrap around the galaxy like faint rings. Others arc across the sky in long curves, stretching tens or even hundreds of thousands of light years. They are not dense or bright. In fact, they are so spread out that they often blend into the background of the galaxy, nearly invisible unless you know exactly what to look for. This is why they are often described as ghosts. From Earth, when we look at the night sky, we mostly see the bright disk of the galaxy. The halo, where stellar streams live, is faint and sparse. Individual stream stars look just like any other star. There is nothing about their brightness or colour that immediately reveals their shared origin. If you only look at light, streams disappear into the crowd. But motion changes everything. Stars in a stellar stream move together. They share the same direction, similar speeds, and related orbits. They behave like a school of fish long after the ocean has erased the shape of the net that once held them. Even when the stream spreads out and becomes visually faint, its motion remains organized. This is where backward motion becomes a powerful tool. When a destroyed galaxy approached the Milky Way from the opposite direction, its stars entered the system, moving backward. As that galaxy was torn apart, its stars were stretched into a stream that still carries that backward motion. Even billions of years later, those stars continue to orbit the galaxy the wrong way, tracing the path of their lost home. Backward motion acts like a highlighter. In a galaxy where most stars move together, a group of stars moving in the opposite direction immediately stands out. Astronomers can follow that shared backward motion across the sky and uncover the faint outline of a stellar stream that would otherwise be invisible. This is why many stellar streams were not discovered through images, but through data, through measurements of position, speed, and direction. Motion reveals structure that light alone cannot. This leads to an important idea. In astronomy, seeing is not always believing. The universe hides much of its history in places that do not shine brightly. Stellar streams are made of old stars. They do not glow like nebulae or young clusters. They quietly orbit, faint and scattered. Their presence is subtle. Without precise measurements, they look like nothing more than random background stars. This is why streams are hard to see. Another reason is time. The longer a stream exists, the more it spreads out. Gravity stretches it thinner and thinner. After billions of years, a stream can become so diffuse that its stars are separated by vast distances. The stream still exists, but it is no longer a clear ribbon. It becomes a whisper. Backward motion keeps that whisper audible. When astronomers map stellar velocities and directions, they can find stars that share unusual motion. When many such stars line up along a path, a stream emerges from the data. It is not drawn in light. It is drawn in motion. This is a fundamental shift in how we understand the galaxy. For centuries, astronomy was about light. Brighter objects were easier to study. Dark, faint structures were ignored because they were invisible. Today, motion has become just as important as brightness, sometimes more important. Stellar streams are proof of that. They tell us that the galaxy is surrounded by the shredded remains of smaller galaxies, that the halo is not empty, that it is filled with long dead structures still drifting through space. Backward moving streams are especially valuable because they are easier to separate from the background. They go against the flow. They refuse to blend in. These streams also help astronomers reconstruct ancient events. By studying their shape, direction, and speed, scientists can work backward to determine where the original galaxy came from, how massive it was, and when it was destroyed. In some cases, astronomers can even estimate how many times the stream has wrapped around the galaxy. This turns stellar streams into historical records. They are not just remnants, they are timelines. Another fascinating detail is that streams are not smooth. They contain clumps and gaps. These features reveal interactions with dark matter and other massive objects. As the stream passes through the galaxy, invisible structures disturb it. The stream bends, ripples, and breaks. By studying these disturbances, astronomers learn not just about the destroyed galaxy, but about the unseen structure of the Milky Way itself. Once again, motion reveals what light cannot. Backward stellar streams are particularly sensitive to these effects because their orbits often take them far from the disk, through regions dominated by dark matter. This makes them powerful tools for mapping the invisible skeleton of the galaxy. All of this comes back to one simple idea. When galaxies die, they do not vanish, they dissolve, and their stars remember. A stellar stream is a memory stretched across space. It is the last echo of a galaxy that no longer exists. Backward motion is the accent that tells us where that galaxy came from and how it entered the Milky Way. Without motion, these ghosts would remain unseen. This changes how we think about destruction in the universe. Destruction is not erasure, it is transformation. The shape is lost, but the story remains. The Milky Way is surrounded by these stories. Long rivers of stars flow silently through its halo, invisible to the eye, but obvious to those who know how to listen. And backward motion is one of the clearest ways to hear them. So when astronomers find stars moving against the galactic flow, they are not just finding odd stars. They are uncovering the outlines of lost galaxies. They are tracing ancient paths written across the sky. Stellar streams are the ghosts of destroyed galaxies, and motion is the only light that reveals them. To understand why backward orbiting stars exist, we have to look beyond what we can see. Stars, gas, and dust make up only a small part of a galaxy's true mass. Most of a galaxy is invisible. This hidden component is called dark matter, and without it, the story of backward stars would make very little sense. Dark matter does not glow. It does not absorb or emit light. Telescopes cannot photograph it directly. But dark matter has gravity, and gravity leaves fingerprints everywhere. When astronomers talk about dark matter halos, they are describing enormous, invisible structures that surround galaxies like vast, unseen cocoons. Imagine the visible galaxy as a bright city at night. The lights show you where the buildings are, but not where the land is shaped, where the hills rise, or where the valleys dip. Dark matter is that invisible landscape. It defines the shape of the terrain long before the city lights appear. Every large galaxy sits inside a massive dark matter halo. This halo extends far beyond the visible disk, reaching deep into space. In fact, most of the galaxy's mass is not in the stars at all, but in this invisible halo. The stars are simply moving decorations embedded inside a much larger gravitational structure. This matters because gravity controls motion. Stars do not orbit just because of the visible galaxy. They orbit because they are responding to the combined gravitational pull of everything around them, including dark matter. The halo acts like an enormous gravitational net, shaping the paths that stars can take. When a small galaxy approaches a larger one, it does not first encounter the bright disk or glowing stars. It encounters the dark matter halo. Long before stars interact, dark matter interacts. The two halos begin to overlap, tugging on each other, slowing the smaller galaxy down and pulling it inward. This is why mergers follow dark matter paths. The visible collision we imagine is actually the final act. The real interaction starts earlier, invisibly, when dark matter halos meet. The smaller galaxy is captured not by the stars of the larger galaxy, but by its dark matter halo. Once trapped, there is no escape. As the smaller galaxy spirals inward, its stars follow the path carved by dark matter. They are dragged along invisible highways shaped by gravity. These paths determine how the galaxy is torn apart and where its stars end up. If the incoming galaxy approaches from a direction opposite to the main rotation of the larger galaxy, its stars will enter the system with backward motion. Dark matter does not care about direction. It does not enforce order. It simply pulls. This is why backward stars are often found in the halo. The halo is dominated by dark matter. It is where dark matter's influence is strongest and least disturbed by the orderly rotation of the disk. Stars moving through this region are tracing the shape of the dark matter halo itself. In this sense, backward stars are not just stars, they are test particles. Their motion reveals the invisible structure they're moving through. This is one of the most powerful ideas in modern astronomy. We cannot see dark matter directly, but we can see what it does. And what it does is guide motion. Backward stars often move on long looping orbits that take them far above and below the galactic disk. These orbits are shaped by the dark matter halo. The stars slow down, speed up, and change direction in ways that only make sense if there is far more mass present than we can see. By mapping these motions, astronomers can infer the size, shape, and distribution of dark matter. This turns backward stars into tools. They help scientists answer questions that would otherwise be impossible. How round is the dark matter halo? Is it stretched? Is it clumpy? Does it have streams and substructures of its own? These questions matter because dark matter is the scaffolding on which galaxies are built. Another important detail is that dark matter halos are not smooth. They contain subhalos, smaller clumps of dark matter left over from earlier mergers. When a stellar stream passes through one of these invisible clumps, it gets disturbed. The stream bends, ripples, or breaks. Backward-moving streams are especially useful for detecting these disturbances because they often travel far from the disk, where the influence of dark matter is clearer and less masked by other effects. In this way, backward stars allow astronomers to see the unseen. They reveal the hidden architecture of the galaxy. They show where gravity is strongest, where it changes, and where invisible mass is concentrated. This also explains why backward motion can survive for billions of years. Dark matter halos are stable. They change slowly. Once a star is placed on a backward orbit within the halo, there is little to disturb it. The disk's orderly rotation does not dominate here. The halo preserves memory. Without dark matter, this entire story would fall apart. Galaxies would not have enough gravity to hold onto fast-moving stars. Mergers would behave differently. Streams would dissolve quickly. Backward stars would be rare and short-lived. Dark matter makes backward motion possible, stable, and meaningful. It also reshapes how we think about the galaxy itself. The bright spiral we see is only the surface. Beneath it lies a vast, invisible structure guiding everything. Stars, including those that move backward, are passengers as riding through this structure. Their paths determined by forces we cannot directly observe. This is why astronomers say that motion is a form of vision. We cannot see dark matter, but we can watch stars respond to it. Every backward orbit is a line drawn through invisible space, outlining the shape of something we cannot photograph. In a way, backward stars are messengers from the dark side of the galaxy. They move where the disk does not dominate. They travel paths shaped almost entirely by unseen mass. Their motion speaks for what we cannot see. Understanding this adds a new layer to the mystery. Backward stars are not just evidence of ancient collisions. They are probes of the invisible universe. They tell us where galaxies have been, how they grew, and what they are truly made of. So when we study backward orbiting stars, we're doing more than tracking unusual motion. We are mapping the dark skeleton of the galaxy. We are turning gravity into a language we can read. And through that language, the unseen becomes known. Up to this point, backward orbiting stars have sounded like clear outsiders, immigrants from destroyed galaxies that carried their original motion into the Milky Way. In most cases, that picture is correct, but the universe is rarely so simple. Not every star that moves against the galactic flow was born somewhere else. A small but important number of backward stars were likely born inside the galaxy itself and slowly pushed onto unusual paths by forces acting from within. This is harder to understand, rarer to find, and much more subtle, but it adds depth to the story and reminds us that even an orderly galaxy can reshape its own stars over time. The Milky Way is not a rigid object. It is alive with motion and structure. Its disk is not perfectly smooth. It contains spiral arms, waves of density, and a massive bar-shaped structure stretching across the center. Each of these features creates gravitational disturbances. Most of the time, these disturbances are gentle. They nudge stars slightly inward or outward. They tilt or stretch orbits. They heat the disk over billions of years, turning a thin, orderly structure into a thicker, puffier one. In rare cases, those nudges can be dramatic. At the center of the galaxy lies the galactic bar, a long, dense concentration of stars rotating as a single structure. This bar acts like a giant gravitational spoon, stirring the inner galaxy. As it rotates, it transfers energy and angular momentum to nearby stars. Some stars are pulled inward, others are pushed outward. Their orbits become elongated, tilted, and more complex. Over extremely long periods of time, repeated interactions with the bar can significantly alter a star's path. Spiral arms also play a role. They are not solid structures, but moving waves of higher density. As stars pass through these waves, they experience gravitational kicks. Most of these kicks are small, but over billions of years, they add up. A star can slowly migrate across the disk, changing its distance from the center and the shape of its orbit. This process is called radial migration, and it shows that stars do not stay exactly where they are born. However, changing direction entirely is much harder. To flip a star from prograde to retrograde motion using only internal processes requires extreme circumstances. The star must lose a large amount of its original angular momentum and gain new momentum in the opposite direction. The galaxy strongly resists this. Its disk is built to maintain shared rotation. Most disturbances smooth out differences rather than reverse them. This is why internally created backward stars are rare. But rare does not mean impossible. One possible pathway involves repeated gravitational interactions in the inner galaxy, especially near the bar and bulge. Stars that pass very close to the center can experience chaotic gravitational forces. Their orbits can become highly eccentric and strongly tilted. In exceptional cases, a star's orbit can be flipped, turning a once normal star into a retrograde one. Another pathway involves vertical waves rippling through the disk. These waves can be triggered by interactions with satellite galaxies or massive dark matter clumps. When a wave passes through the disk, it lifts stars above and below the galactic plane, tilting their orbits. Most stars eventually settle back into prograde motion, but a few may be pushed onto unusual paths that include partial or even full backward components. These internally produced backward stars tend to share certain traits. They are usually closer to the disk than foreign stars. Their orbits often look messy rather than clean. They may not belong to coherent streams. Their chemical composition often matches the galaxy's native stars, suggesting they formed from the same gas. This is where separating outsiders from locals becomes crucial. Astronomers do not rely on motion alone. They combine multiple clues. Motion tells part of the story, but chemistry tells another. Stars born in different galaxies often have different chemical fingerprints. They formed from gas with different histories, different enrichment levels, and different patterns of heavy elements. A star that moves backward but has chemical traits identical to disk stars is suspicious. It suggests an internal origin. A star that moves backward and carries a chemical signature, unlike the disk, is almost certainly an outsider. Age also matters. Internally flipped stars can be old or young, depending on when the disturbance occurred. Accreted stars are almost always very old. Their ages line up with early epochs of galaxy formation. Location matters too. Stars flipped internally rarely end up deep in the halo. They tend to remain closer to the disk, where the disturbances occurred. Halo stars with strong backward motion are far more likely to be foreign. By combining motion, chemistry, age, and location, astronomers can separate the few locales from the many immigrants. This distinction is important because it prevents oversimplification. Not every strange orbit tells the same story. Some are records of ancient galactic cannibalism. Others are scars left by internal evolution. Together, they show that the galaxy is shaped by both external violence and internal restlessness. The idea that a galaxy can slowly reshape its own stars adds nuance to our understanding of order and chaos. The Milky Way is stable, but not frozen. Over billions of years, even small disturbances accumulate. Bars rotate, waves ripple, orbits stretch, the disk thickens. A few stars are pushed far from their original paths. Still, the key word is few. Internal processes struggle to create true retrograde motion on large scales. They are inefficient at fully reversing direction. This is why the majority of backward stars remain strong evidence of external origins. Internal mechanisms add noise to the picture, but they do not dominate it. This balance matters. It tells us that when we see many stars moving backward together, especially in the halo, we are almost certainly looking at the remains of a destroyed galaxy. When we see a single backward star closer to the disk, we must be more careful. Science advances by learning to tell these stories apart. In a way, this mirrors how history works on Earth. Some ruins tell us about invasions, others tell us about revolutions from within. Both matter. Both shape the present. The galaxy is no different. Not all backward stars are foreign, but most are. The exceptions remind us that galaxies are dynamic systems, capable of surprising internal changes. The rule-breaking stars born at home show how even a stable system can produce anomalies over time. Understanding this distinction strengthens the overall story. It shows that backward motion is not a simple label, but a clue that must be interpreted carefully. It demands context, patience, and multiple lines of evidence. And once those pieces come together, the galaxy reveals itself not as a rigid machine, but as a living system shaped by both outside forces and internal evolution. Backward stars are not all immigrants. Some are locals who are quietly pushed onto strange paths by the slow, persistent shaping of gravity itself. And learning to tell the difference is one of the most delicate and fascinating challenges in modern astronomy. For a long time, backward orbiting stars were mostly an idea. Astronomers suspected they existed, but evidence was limited. Measuring the motion of stars across the sky is incredibly difficult. Stars are far away. Their movement is slow. From Earth, even fast stars appear almost frozen. For decades, scientists could only guess at the full picture. That changed with modern sky surveys. In recent years, astronomers began mapping the Milky Way with unprecedented precision. Instead of just asking where stars are, these surveys asked a deeper question. Where are stars going? By tracking tiny changes in position and measuring speeds along the line of sight, scientists built three-dimensional maps of stellar motion across large parts of the galaxy. What they found was stunning. Hidden within the Milky Way are thousands of stars moving the wrong way. These are not rare mistakes or measurement errors. They form clear patterns, groups of stars sharing backward motion, stars on highly tilted orbits, streams of stars sweeping through the halo against the galaxy's rotation. The evidence is overwhelming. Backward stars are real, and they are an important part of our galaxy. Even more surprising is how close some of them are. Backward stars are not just distant objects lurking at the far edge of the halo. Some pass relatively near our cosmic neighborhood. They move through regions not too far from where the Sun orbits. We are not observers watching this from the outside. We live inside a galaxy filled with these ancient travelers. This realization changes perspective. The Milky Way is not a smooth, uniform system. It is layered with history. The stars around us are not all from the same family. Some were born here, others arrived long before Earth existed. Their presence nearby means the evidence of ancient collisions is not locked away in distant space. It surrounds us. Astronomers analyzing these stars notice something important. Many backward stars share similar properties. They tend to be old. They often have low amounts of heavy elements, suggesting they formed early in the universe, before many generations of stars enriched the galaxy with metals. Their motions are elongated, tilted, and often extreme. These traits point to a shared story. They are not random individuals. They are survivors of ancient events. By grouping stars based on motion and chemistry, astronomers uncovered the remains of long-destroyed galaxies. Some of these galaxies were absorbed so completely that only their stars remain, scattered through the halo and inner regions of the Milky Way. Their shapes are gone, their names are lost, but their motion still tells us they were once separate worlds. Backward motion is often the clearest signature. One of the most powerful discoveries is that many backward stars belong to large coherent structures. They are not isolated oddities, they move together as if still bound by a shared past. This strongly supports the idea that the Milky Way experienced major mergers early in its history. Not just small snacks, big collisions. These mergers were violent enough to reshape the galaxy, puffing up the halo, thickening the disk, and redistributing stars across vast distances. The Milky Way we see today is the survivor of those events. It absorbed its rivals and carried on. This is why astronomers sometimes describe our galaxy as a survivor galaxy. It lived through chaos. It endured collisions. It grew stronger by assimilation. Backward stars are witnesses to that survival. Another important discovery is that backward stars are not evenly distributed. They cluster in certain regions. This uneven distribution matches predictions from simulations of galaxy formation. When a galaxy absorbs another, the incoming stars do not spread out evenly. They follow specific paths. They linger in streams and clouds. Over time, these structures fade but never fully disappear. Seeing these patterns in real data was a major breakthrough. It confirmed that the Milky Way formed the way scientists thought it did. Not peacefully, but through repeated mergers and disruptions. Perhaps the most humbling part of this discovery is how personal it feels. We often imagine cosmic events as distant and abstract, but backward stars remind us that the history of the Milky Way is our history too. The Sun orbits within a galaxy shaped by destruction. The night sky we see is the result of ancient violence, softened by time. Some of the stars you see tonight may not belong here at all. They may have formed in a different galaxy, under a different sky, orbiting a different center. They may have been carried here by gravity, surviving the death of their home and settling into a new one. This realization deepens the story of the Milky Way. It is not just a spiral of stars, it is a mosaic of origins, a blended archive of many smaller galaxies that no longer exist. Modern surveys did more than confirm backward stars. They gave astronomers confidence that motion is a reliable storyteller, confidence that the halo is a record of the past, confidence that we can reconstruct ancient events from subtle clues. This has transformed astronomy into a kind of cosmic archaeology. Instead of digging into the ground, scientists dig into data. Instead of pottery shards, they find velocity patterns. Instead of ruins, they find stellar streams. Backward stars are among the most valuable artifacts in this archaeological record. They tell us when mergers happened. They tell us how massive the incoming galaxies were. They tell us from which direction they arrived. They even help estimate how the Milky Way's dark matter halo is shaped. All of this from stars simply moving the wrong way. Perhaps the most important lesson is this: the Milky Way did not become what it is by avoiding danger. It became what it is by surviving it. It absorbed others. It was reshaped. It adapted. And we live inside the result. When you look up at the night sky, you are not just seeing stars. You are seeing survivors, immigrants, and locals all mixed together. Some stars are telling the story of calm formation. Others are telling the story of ancient catastrophe. Backward stars are among the loudest storytellers. They remind us that the galaxy has a past filled with struggle and transformation. They remind us that peace often comes after chaos. And they remind us that even in a universe governed by simple laws, the outcomes can be rich, layered, and deeply surprising. We live inside a survivor galaxy, and thanks to backward orbiting stars, that survival story is no longer hidden. Detecting backward motion in stars is one of the most delicate achievements in modern astronomy. It is not something you can see by looking at the sky for a few nights, or even a few years. Stars are incredibly far away. Even the fastest ones move so slowly across our sky that to the human eye, they appear completely still. Yet astronomers have learned how to measure these tiny motions with astonishing precision, turning nearly invisible shifts into a detailed map of how our entire galaxy moves. The first idea to understand is simple. Stars are not fixed points. They're constantly moving through space. The challenge is scale. When a star moves, the change in its position is incredibly small when viewed from Earth. It is like watching a coin move a few millimeters from thousands of kilometers away. Detecting that movement requires patience, accuracy, and powerful technology. Astronomers break a star's motion into two main parts. One part is how the star moves across the sky, sideways from our point of view. This is called proper motion. The other part is how the star moves toward us or away from us. This is called radial motion. To understand backward orbits, scientists need both. Proper motion is measured by comparing images of the sky taken years apart. Astronomers take a precise picture of a star's position, then take another picture years later, and then another. By stacking these images and measuring tiny changes, they can see the star slowly drifting against the background. The movement is usually measured in fractions of an arc second, a unit so small it is hard to imagine. Yet over time, these tiny shifts reveal direction and speed across the sky. Radial motion is measured using the Doppler effect. This effect is easier to explain with sound. When an ambulance drives toward you, its siren sounds higher in pitch. When it drives away, the pitch drops. Light behaves the same way. When a star moves toward us, its light is slightly compressed, shifting toward blue. When it moves away, its light stretches, shifting toward red. Astronomers analyze a star's light by splitting it into a spectrum, like a rainbow. Inside that spectrum are dark lines created by elements in the star's atmosphere. These lines act like markers. When the star moves, the lines shift slightly. By measuring that shift, scientists can tell how fast the star is moving toward or away from Earth. Neither proper motion nor radial motion alone tells the full story. Proper motion shows sideways movement. Radial motion shows forward or backward movement along our line of sight. Only by combining both can astronomers reconstruct a star's true three-dimensional motion through space. This is where the real magic happens. Once scientists know how a star moves in 3 dimensions, they can calculate its orbit around the galactic center. They can determine whether it moves with the galaxy's rotation or against it. This is how backward stars are identified, not by guesswork, but by careful measurement and geometry. Turning these tiny motions into a galactic map is a monumental task. Astronomers collect motion data for millions of stars. They correct for Earth's own movement around the Sun. They correct for the Sun's movement within the galaxy. They transform everything into a common reference frame centered on the Milky Way. What emerges from this process is not a picture, but a living map. Arrows showing direction, colors showing speed, patterns revealing structure. In these maps, backward stars stand out clearly. While most arrows point one way, a small population points the opposite way. These stars are not scattered randomly. They cluster, they align, they form streams and clouds. Their backward motion is unmistakable. This ability to see backward motion did not exist until recently. For most of human history, stars were dots of light. Even with early telescopes, astronomers could only measure positions, not motion. The breakthrough came with long-term observation and space-based instruments. Space telescopes changed everything. Above Earth's atmosphere, telescopes avoid distortion from air, weather, and temperature changes. They can measure positions far more accurately. Over time, they can detect motions that would be impossible to see from the ground. Equally important is computing power. Measuring the motion of millions of stars generates enormous amounts of data. Modern computers allow astronomers to process this data, correct errors, and find patterns that would be invisible otherwise. Spectroscopy technology also advanced dramatically. Instruments became sensitive enough to detect extremely small Doppler shifts. This allowed scientists to measure stellar speeds with incredible precision, sometimes to within a few meters per second, across vast cosmic distances. All of these technologies combine to unlock the galaxy's motion. What makes this especially remarkable is how indirect the process is. Astronomers are not watching stars move in real time. They are measuring tiny clues, shifts in light and position, and using physics to reconstruct motion across tens of thousands of light years. Backward motion emerges not as a dramatic reversal, but as a subtle statistical truth. Another important point is time. Many surveys operate for decades. They rely on patience. The longer the time span between observations, the more accurate the proper motion becomes. Some of the most valuable discoveries came from comparing data sets separated by 20 years or more. This long view allows astronomers to see what the galaxy is doing, not just what it looks like. It also explains why backward stars were missed for so long. Without long-term data and precise instruments, their motion blended into noise. Only now do we have the clarity to separate signal from background. One of the most powerful aspects of this work is consistency. When different methods agree, confidence grows. Proper motion data matches Doppler measurements. Independent surveys see the same backward populations. Models predict the same patterns observed in reality. This agreement confirms that backward stars are not artifacts or errors. They are real components of the Milky Way. It also shows that motion is one of the most reliable tools in astronomy. Light tells us what stars are like. Motion tells us where they came from. By detecting backward motion, scientists turn the galaxy into a dynamic system rather than a static image. They see it as a flow of matter shaped by gravity over billions of years. Perhaps the most awe-inspiring part of this process is scale. Tiny shifts in light and position, measured with incredible care, reveal events that happened billions of years ago. A fraction of a wavelength shift can point to the destruction of an entire galaxy in the distant past. This is the power of modern astronomy. It does not rely on spectacle, it relies on precision. Through careful measurement of motion, astronomers have uncovered the hidden history of the Milky Way. They have revealed backward stars not as curiosities but as key evidence of mergers, evidence of survival, evidence that our galaxy is still carrying the memory of its past in the way its stars move today. In the end, detecting backward motion is not just about technique, it is about perspective. It is about learning to see the universe not only as it appears now, but as it has evolved over deep time. By turning tiny shifts into galactic maps, scientists have learned to read the galaxy like a story written in motion. And backward stars are some of the most important sentences in that story. Backward orbiting stars may look ordinary at first glance. They shine like any other star. They follow gravity like any other star. But scientifically, they are among the most valuable objects in the galaxy. Astronomers care about them deeply because these stars do something rare and powerful. They preserve information from a time that no longer exists. They act as time capsules, carrying the conditions of the early universe forward into the present. Most astronomical objects change over time in ways that erase their past. Gas clouds collapse and form new stars. Young stars age and evolve. Galaxies collide, reshape, and settle into new forms. Shape, brightness, and structure are temporary. Motion is not. Motion is stubborn. Once set, it is incredibly difficult to fully erase. This is why backward stars matter so much. A backward star is not just moving differently, it is remembering differently. When astronomers look at these stars, they are effectively looking billions of years into the past. Many backward stars formed very early in cosmic history, when the universe was young and galaxies were still assembling. At that time, the universe looked nothing like it does now. There were fewer heavy elements, star formation was intense, galaxies were smaller, messier, and more numerous. Collisions were common. Backward stars formed in that environment. Because they preserve their original motion, they preserve clues about that environment. Their orbits tell us how galaxies moved relative to each other long before the Milky Way settled into its current shape. Their chemistry tells us what kinds of elements existed at the time of their birth. Together, motion and composition form a record that cannot be recreated any other way. This makes backward stars uniquely powerful tools for learning about the early universe. We cannot travel back in time. We cannot directly observe the first stages of galaxy formation, but we can study stars that were born during those stages and never forgot where they came from. Backward stars allow astronomers to test theories about how the universe evolved from chaos into structure. One of the most important uses of backward stars is reconstructing lost galaxies. When a small galaxy is swallowed by a larger one, its shape disappears, its gas is absorbed, its core dissolves. After a few billion years, there is no visible object left to study, but the stars remain. And if those stars share unusual motion, especially backward motion, astronomers can group them together and recognize them as the remains of a single destroyed system. This is like reconstructing a broken vase from scattered shards. By studying the orbits of backward stars, scientists can determine how massive the original galaxy was, how fast it was moving, and from which direction it approached. They can estimate when the merger happened and how violent it was. In some cases, they can even trace the original orbit of the lost galaxy before it was destroyed. This is extraordinary. It means astronomers can study galaxies that no longer exist. Backward stars are often the clearest markers of these lost systems because they stand out so strongly against the galaxy's normal rotation. Without them, many ancient mergers would be invisible. The Milky Way would look quieter and simpler than it really is. Another reason backward stars are scientifically precious is that they help test models of galaxy formation. Theories and simulations predict that large galaxies should grow by absorbing many smaller ones. These simulations produce specific patterns of motion in the halo, including populations of retrograde stars. When astronomers observe backward stars in the real Milky Way, they can compare those observations to simulations. Agreement strengthens confidence in the models. Disagreement reveals gaps in understanding. Backward stars are not just evidence, they are tests. They help answer questions like how fast the galaxy grew, how many mergers it experienced, and how those mergers shaped the disk and halo. They help explain why the Milky Way looks the way it does today. Motion is the key to all of this. Light tells us what stars are made of. Motion tells us where they came from. Together they form a historical record that is far more detailed than either alone. This is why astronomers often say that motion is historical evidence. In human history, we rely on documents, artifacts, and ruins. In galactic history, we rely on orbits. A backward orbit is like a document that survived every attempt to erase it. It tells a story without words. Backward stars also help astronomers understand dark matter. Because these stars often travel far into the halo, their motion is strongly influenced by the galaxy's dark matter structure. By tracking their paths, scientists can infer how dark matter is distributed, how smooth or clumpy it is, and how it responds to mergers. This makes backward stars doubly valuable. They reveal both visible and invisible history. Another reason astronomers care deeply is rarity. Backward stars are not common compared to normal stars. Each one represents an unusual story. Finding them requires precision, patience, and large data sets. When astronomers identify a population of backward stars, it often leads to major discoveries. New stellar streams, evidence of previously unknown mergers, revisions to the galaxy's timeline. These stars punch far above their weight scientifically. They also challenge assumptions. For a long time, the Milky Way was thought to have had a relatively calm past. Backward stars helped overturn that idea. They revealed that the galaxy experienced significant mergers early on. They showed that even our local stellar neighborhood contains immigrants from other galaxies. This changed how astronomers think about where we live. We do not live in a pristine, untouched system. We live in a galaxy built from fragments. Backward stars also connect small-scale physics to large-scale history. A star's orbit depends on gravity, mass, and energy. Those same factors govern galaxy collisions, dark matter halos, and cosmic structure formation. By studying a single star's motion, astronomers link the physics of individual objects to the evolution of the entire universe. This is rare in science. Few objects bridge so many scales so effectively. Perhaps the most compelling reason astronomers care is philosophical. Backward stars remind us that the universe remembers. Even when shapes vanish and structures dissolve, information persists. It is encoded in subtle ways, waiting to be decoded. These stars teach patience. They teach humility. They show that the present is shaped by events unimaginably distant in time. When astronomers spend years measuring tiny motions, they are not just chasing data. They are listening to ancient voices. Backward stars speak softly, but what they say is profound. They tell us that the universe is built through struggle and survival. They tell us that history is written not just in light, but in motion. They tell us that the Milky Way is not a simple spiral, but a layered archive of cosmic memory. This is why these stars are scientifically precious. They are time capsules drifting through space. They are evidence that cannot be forged. They are survivors carrying the story of the early universe into the present. And for astronomers trying to understand where everything came from, that makes them priceless. Whenever the idea of stars orbiting a galaxy backward comes up, it is almost impossible to avoid dramatic interpretations. Science fiction has trained us to expect rebellion, explosions, sudden reversals, and violent twists whenever something breaks the rules. A star going the wrong way sounds like a cosmic act of defiance. But this is where reality and fiction sharply diverge, and understanding that difference is essential if we want to truly appreciate what backward stars mean. The first and most common myth is the idea that stars somehow choose to rebel. Stars do not make decisions. They do not resist. They do not fight gravity out of anger or will. A backward orbiting star is not a troublemaker or an anomaly with intention. It is simply following the path set for it by gravity long ago. Once a star is placed on an orbit, it will keep following that orbit unless an enormous force acts on it. There is no awareness involved, only physics. Calling these stars rebels may sound poetic, but it hides the real story. The truth is far more interesting. These stars are not breaking the rules. They are obeying them perfectly. The rules just allowed many possible outcomes. Another widespread misconception is that backward motion requires explosions or sudden catastrophic events. This idea comes straight from movies. In fiction, direction changes are dramatic. Things flip instantly. Galaxies collide in bright flashes. Stars are flung violently in all directions. In reality, almost nothing in space happens suddenly. Galactic events unfold slowly, over timescales so long that human language struggles to describe them. When a galaxy is absorbed by another, its stars do not explode outward. They are gently stretched, pulled, redirected. The process is quiet, gradual, and relentless. A backward orbit does not come from a single moment of chaos. It comes from a long history of gravitational influence. This is one of the hardest ideas to accept. The universe is dramatic without being loud. Another sci-fi misunderstanding is the belief that backward stars threaten the stability of the galaxy. Fiction often portrays anything wrong as dangerous. A star moving against the flow must be destabilizing the system, right? In reality, backward stars are dynamically stable. Many have been orbiting this way for billions of years. They are not tearing the galaxy apart. They are not causing destruction. The galaxy is large enough and massive enough to absorb these differences without issue. Backward motion is unusual, not dangerous. There is also a popular misconception that backward stars are rare freak accidents. Something went wrong, something broke, something glitched. The truth is the opposite. Backward stars are expected outcomes of galaxy formation. Modern simulations predict them. Observations confirm them. They are not errors in the system, they are signatures of how the system works. Science fiction often simplifies complexity by turning it into spectacle. Reality does the opposite. Reality hides complexity beneath calm surfaces. Another exaggerated idea is that stars can flip direction suddenly due to some exotic force or energy burst. This makes for exciting storytelling, but it ignores basic physics. Changing the direction of a star's orbit requires altering its angular momentum. Doing that takes immense gravitational interaction over long periods of time. There is no switch that flips a star from forward to backward overnight. Even the most violent galaxy collisions do not cause instant reversals. They reshape orbits slowly, gradually, predictably. This is why backward stars are so powerful scientifically. They are not the result of noise or chaos. They are the result of consistent physical processes playing out over deep time. Science fiction also tends to exaggerate scale in the wrong way. In movies, galaxies are treated like small objects. Collisions look like car crashes. Stars zip past each other like sparks. In reality, galaxies are mostly empty space. When two galaxies collide, individual stars almost never collide with other stars. The interaction is dominated by gravity, not impact. This means the violence of galactic cannibalism is structural, not explosive. Shapes dissolve, orbits change, systems merge, but stars themselves continue shining, largely unaffected at a local level. Backward stars emerge from this quiet violence. Understanding real cosmic scale changes everything. Events that look dramatic in fiction are actually subtle in reality. Events that look subtle in reality are often the most important. Another myth is that backward stars somehow violate cosmic order. This idea comes from assuming the galaxy is supposed to be perfectly organized. But the universe does not aim for perfection. It evolves, it experiments, it leaves behind leftovers. Order emerges from chaos, but chaos never fully disappears. Backward stars are not disorder invading order. They are reminders that order was built from disorder in the first place. Reality is more impressive than fiction because it does not need exaggeration. A single backward star can tell astronomers about a galaxy that no longer exists. It can reveal a merger that happened billions of years ago. It can map invisible dark matter. It can test models of cosmic evolution. No explosion is needed to make that meaningful. No dramatic reversal is required. Just motion. Science fiction often focuses on the present moment. What is happening now? Reality rewards patience. The most important events in the universe leave traces that only make sense when viewed across immense spans of time. Backward stars are slow storytellers. They whisper instead of shout. They do not demand attention. They reward careful listening. Respecting real cosmic scale also means respecting how long the universe takes to change. Human intuition is shaped by seconds, minutes, and years. Galactic intuition must be shaped by millions and billions of years. When you adopt that perspective, backward motion stops being shocking and starts being inevitable. Of course, science fiction has value. It inspires curiosity. It sparks imagination. It draws people towards science. But it also creates expectations that reality does not try to meet. Reality does not need laser beams or collapsing spirals to be awe-inspiring. A star quietly orbiting the wrong way for 10 billion years is far more profound. It tells us that the universe remembers. It tells us that history is never fully erased. It tells us that the Milky Way is not a static object, but a layered record of survival. When we strip away the myths, what remains is something deeper and more honest. Backward stars are not rebels. They are witnesses. They are not products of explosions. They are products of time. They are not threats to order. They are proof of how order emerged. Understanding this requires letting go of dramatic shortcuts and embracing the true scale of the cosmos. And when we do, we discover that reality does not fall short of fiction. It surpasses it. Because in reality, the most extraordinary stories are written quietly, patiently, and permanently into the motion of stars that simply refuse to forget where they came from. Backward orbiting stars do more than explain a strange detail of galactic motion. They teach us how the universe actually works. They reveal a truth that feels uncomfortable at first but becomes beautiful once understood. Growth in the universe does not come from calm perfection. It comes from disruption, from loss, from destruction that slowly turns into structure. When we study backward stars, we are studying this process in its purest form. Galaxies do not grow by gently adding pieces in neat layers. They grow by colliding, tearing, absorbing, and surviving. Every large galaxy is the result of many smaller ones that no longer exist. Their destruction was not a failure. It was a step in a larger process. Backward stars are living evidence of this. Each one represents a system that lost its identity so a bigger structure could form. This is growth through destruction. It is easy to imagine growth as something positive and clean, but on cosmic scales, growth is violent. Small galaxies fall into larger ones. Their shapes are erased, their gas is stripped, their stars are scattered, and yet nothing is wasted. Everything becomes part of something new. Backward stars show us that destruction in the universe is not the end of the story. It is how the story continues. From that destruction, order emerges. At first, galaxy mergers are chaotic. Orbits are stretched. Directions are mixed, shapes are distorted, but gravity is patient. Over billions of years, chaos settles, random motion smooths out, disks form, spiral arms appear, the galaxy finds a new balance. What we see today as a calm, rotating spiral is the final result of countless earlier disruptions. Backward stars are reminders of the chaos that came before the calm. They show us that order is not the natural starting point of the universe. Order is the outcome. It is built slowly from disorder. Every backward orbit is a scar that never fully healed, a reminder that the present state of the galaxy required enormous upheaval to exist at all. This changes how we should think about galaxies. They are not finished objects. They are evolving systems. They are processes, not products. The Milky Way today is not the Milky Way of 10 billion years ago, and it will not be the Milky Way of 10 billion years in the future. It is constantly changing, constantly reshaping itself through internal evolution and external interactions. Backward stars are snapshots of earlier versions of this ongoing process. When astronomers study these stars, they are not just cataloguing odd motions. They are watching evolution in action frozen into trajectories that span cosmic time. They see how galaxies assemble themselves piece by piece. They see which processes dominate early on and which take over later. They see how structure emerges from complexity. This is where motion becomes more powerful than images. Images show us what the universe looks like now. Motion shows us how it became that way. A photograph of the Milky Way reveals a beautiful spiral. It does not reveal the dozens of galaxies that were consumed to build it. It does not show the timing of those mergers. It does not show the directions from which those galaxies arrived. Motion does. Backward stars encode all of that information. Their orbits are like arrows pointing into the past. By tracing those arrows, astronomers can reconstruct events that left no visible shape behind. This is why motion tells better stories than images. Images can deceive. A galaxy can look calm and orderly while hiding a violent history. Motion cannot hide. It carries memory forward even when form fades. A disk can reform. A halo can smooth out. But a star's trajectory still remembers where it was set in motion. Backward stars are storytellers written in velocity instead of light. They tell us that the universe is not forgetful. It does not erase its past, it buries it in subtle ways. It hides history in places that require patience and precision to uncover. When we learn to read motion, we gain access to those hidden chapters. This leads to one of the most profound lessons backward stars teach us. The universe remembers everything. Not in the way humans remember, with conscious thought or recorded history, but in the way physical systems preserve information. Energy is conserved. Momentum is conserved. Motion persists. Even when structures collapse and identities vanish, the consequences remain. A backward orbit is not an accident. It is a preserved outcome of an ancient event. This idea reshapes how we think about time. In everyday life, the past feels gone. In the universe, the past is still moving around us. It is still shaping the present. The stars near us today may have been set on their paths before our planet existed. Their motion links us directly to events that happened billions of years ago. This connection between past and present is not poetic exaggeration. It is physical reality. Backward stars also teach us humility. They show us that the universe operates on scales far beyond human intuition. Events that seem rare to us are common on cosmic timescales. Destruction that would be catastrophic on human scales is routine in galaxy formation. Survival is not about avoiding chaos. It is about absorbing it and continuing. The Milky Way is not special because it avoided collisions. It is special because it endured them. Backward stars are proof of that endurance. They also teach us restraint. It is tempting to look for drama in the universe. Explosions, sudden changes, clear villains and heroes. But the universe tells its most Important stories slowly, quietly, through steady motion that only becomes meaningful when studied carefully. This is a different kind of awe. It is the awe of deep time. It is the awe of systems so large and so old that they still carry the imprint of their birth conditions. It is the awe of realizing that nothing truly disappears. It only changes form. When astronomers study backward stars, they are not just learning about stars. They are learning about the nature of growth, memory, and evolution on the largest possible scale. They are seeing how chaos and order are not opposites, but partners in creation. The universe does not choose between them. It uses both. Backward stars remind us that what looks like disorder today may become the foundation of order tomorrow, that what appears calm now may be hiding a turbulent past. That beauty often emerges from processes that are anything but gentle. In the end, these stars teach us to change how we see the cosmos, not as a static backdrop, but as a living system shaped by time, gravity, and memory. A system where motion matters more than appearance, where history is written into trajectories, where nothing is truly forgotten. The universe remembers everything. Backward stars are simply brave enough to show us how. When we reach the end of this journey, something subtle happens. The galaxy stops feeling like a picture and starts feeling like a voice, not a loud one, not dramatic, a quiet, steady voice that has been speaking for billions of years, long before anyone was there to listen. Backward orbiting stars are part of that voice. They are messengers from the past, still moving, still tracing paths set in motion when the universe was young. We often think of stars as timeless objects, fixed points in the sky, reliable lights that guide navigation and inspire stories. But the truth is far more intimate. Stars move, they remember, and in their motion, they carry messages that no image can hold. Every backward star is a sentence written in gravity, a phrase composed in velocity, a memory that refused to fade. These stars are not shouting their history, they are whispering it. Motion is their language. It is easy to forget that motion can be a form of communication. In daily life, we read motion instinctively. A crowd flowing one way tells us something is happening. A single person moving against that flow catches our attention immediately. In the galaxy, the same logic applies. Billions of stars moving together define the norm. A few moving the other way speak up without making a sound. Backward stars do not need brightness or explosions to matter. Their language is direction, speed, orbit. By learning to listen to that language, astronomers have uncovered a history that would otherwise remain invisible. They have learned that the Milky Way is not a pristine design or a finished masterpiece. It is a survivor. Our galaxy did not grow by avoiding danger. It grew by enduring it. It collided. It absorbed. It was reshaped again and again. Smaller galaxies were torn apart. Their stars were scattered. Their identities were lost. But their motion lived on. Backward stars are proof that survival leaves marks. Not scars you can see easily, but patterns you can measure if you know how to look. Seeing the Milky Way as a survivor changes perspective. Perfection implies stillness, completion, a final form. Survival implies history, struggle, adaptation. The galaxy we live in is not perfect. It is layered, messy, rich with remnants, and that is exactly what makes it interesting. Every backward orbit is a reminder that calm does not mean simple, and beauty does not require a peaceful past. Understanding motion changes how we see everything. If we only looked at images, we would miss most of the story. We would admire the spiral arms and think we understand the galaxy, but images freeze time. Motion restores it. Motion turns the galaxy from an object into a process. It reveals that what we see now is just one frame in a very long film. Once you understand this, the night sky feels different. Those stars are not just shining, they are traveling. They are following paths laid down before Earth existed. Some were born here, some arrived as strangers, some still move to rhythms set by galaxies that no longer exist, and all of them are participating in a slow, continuous dance shaped by gravity and time. This perspective invites humility. We are small, not just in size, but in time. Our entire recorded history is a blink compared to the journeys traced by these stars. Yet we are capable of understanding them. We can measure tiny shifts in light and position and turn them into stories about the birth and growth of galaxies. That ability is remarkable. It also invites patience. The universe does not rush to explain itself. It reveals its secret slowly, to those willing to watch carefully and wait. Backward stars were always there. They did not suddenly appear when we noticed them. What changed was our ability to listen. Listening to the galaxy's memory does not give us neat endings. It does not offer final answers. It offers context. It tells us that the universe is not a place where everything resets. It is a place where consequences persist, where the past continues to move through the present, where nothing truly disappears. This idea can feel unsettling or comforting, depending on how you see it. It means that chaos leaves traces, but it also means that survival leaves meaning. Backward stars are not errors to be corrected. They are chapters that remain readable. And perhaps that is the most powerful lesson of all. Understanding motion does not just change how we see galaxies. It changes how we think about history itself. It reminds us that history is not always visible. It is often hidden in patterns, in trajectories, in the quiet persistence of things set in motion long ago. So when you look up at the night sky after this, you might imagine something different. Not a static dome of lights, but a living archive, a place where stars are still carrying messages from ancient times, where some move with the flow and some move against it, and where both are equally important to the story. The galaxy does not need to speak loudly to be heard. It speaks through motion, through stars that refuse to forget. And as we learn to listen more carefully, we do not reach a final conclusion. We reach a deeper sense of wonder, the kind that does not demand answers, but invites curiosity. The kind that reminds us that the universe is not finished telling its story. We are simply beginning to understand how to listen.